So in December of last year, there was an announcement that there would be an upcoming programming competition. And the goal of this competition would be to detect and track comets in a series of images acquired from the Solar and Heliospheric Observatory. This is essentially a satellite out in space that takes images of the sun, and it just so happens that it is also able to capture comets as they enter its field of view. So I participated in this competition. It was about a month long in duration. It started on January 17 and it concluded on February 14. So this was essentially a machine learning / data science type of competition. They provided an enormous amount of data. There were about 2,000 data sets in the training set alone, with each data set comprised of between 5 and 30 images on average. So here, as you can see, as I scroll through this list here, at the time that I took the screen recording, there were about 500 participants, and it eventually grew to 600 participants in total as the competition progressed. So I was actually fortunate enough, hard work paid off. I was able to place first in this competition. So I figured that some of you might be interested to learn what it is that I came up with, my approach, how it works. And so I'll share details of that in just a moment. Again, with this competition, your goal is to come up with an algorithm to detect and track comets. And so the output of that algorithm then is a list of those detections, with each one having an associated quality score. So they essentially evaluate your algorithm by sorting your list of detections by their associated quality score. And the idea here is that you would have your true positives at the top of the list, and then eventually you might have some false positives at the end of the list. So again, this was a fun competition. I learned a lot. There was a lot of data to look at and analyze, and so it being about a month long in duration, there was a lot that could happen in that time frame, but I kept at it. And here you can see this is earlier on in the competition. I ran my algorithm on there's 2,000 data sets in the training set. You can see it came back with a score of 53.5, which might not sound particularly good on the surface. However, that was actually a factor of 10 higher than what others were submitting at the time. Now, as the competition progressed, then others would start to get higher and higher scores. But I eventually wound up with a score of around 66, which again was the highest score overall. So that was pretty good. Here you can see the output of my algorithm at the time. This was, again, you see lots of true positives at kind of the start of the list, and as you progress and scroll farther, you start to see some false positives, and then near the end of the list, at the end of the output, you start to have more and more false positives. So again, that's kind of how it works. So now I'll go into some more details on how my approach works and what I came up with. And again, this is actually now also a module available in the new version 9 of Tycho. So if you are interested to follow along, you can feel free to do so. So with that, let's go ahead and get started. Okay, so I want to first start off with one of the example data sets. This would be one of the data sets provided in the competition. So this is Comet number 4. And the reason I have chosen this data set is that it is representative of most of the data sets encountered throughout the competition. So it is an example of one of the faint objects. It has a typical number of images. Here you can see there are 10 images in this data set, each of which has about 25 seconds of exposure time, and the typical delta time, the typical spacing from one image to the next, is about 12 minutes. Now there are some instances where you might have 24 or 36 minutes of interval from one image to the next, but typically it's about 12 minutes. And as you can see, the total time here is 2.4 hours. So these are just some numbers to keep in mind as I go through this example. So as most of you might be familiar with, so this is the Tycho software, and I'm going to load up these images into the image viewer. So as I zoom out here, you can see this is the raw data. This is the first image in the sequence. Now if I wanted to, I could go ahead and animate these frames, and you can kind of get an idea of what that looks like. So here's again the raw image data. You can kind of see it almost looks like a video sequence when you animate the frames in this fashion. So it's kind of cool to look at that. That's again the raw data, but it's not very useful for the purpose of detecting objects. In fact, again, this comet number 4 here, I happen to know its location on the first frame, so I'm going to center on that coordinate 164.9. That's the position of the comet on the first image. Now as I zoom into this location here, you can't really see anything at all. It doesn't really look like there's anything there, and again that's because this is the raw data. Now I can attempt to adjust the contrast information and the intensity, and maybe try to bring out a little bit of detail here, but with even just a little bit of video compression, you probably can't really see any detail at all, especially when this is uploaded to a streaming, a video streaming platform. So this is the object, but again, it's very faint, and you would have a hard time extracting it from the raw image data. But that's what I'm going to show in this video, is what I did to refine this data, what I did to help extract these kind of objects of interest. So let's go ahead and take a look at that. Again, this is version 9 of the Tycho software. So I have added a new module in this version, SOHO Comet Search. This is again the Solar and Heliospheric Observatory. So if you open up this module, you're presented with a new window, and we can basically choose a number of options here, what we want to look at. So again, the raw image data, you can choose that as an option. But let's go ahead and take a look at the background subtract. So this would be the result of having subtracted the background information on each image. Now what I mean by that, just to go into a bit more detail, is that basically the background image here would be the result of having stacked all of these images here, and then you compute a new image. So I actually first start off by scaling the images. So I will scale them to some normalized value. In other words, I compute what is the background level of each image, and then I compute a median background level, and then I scale all of the images so that they each have their background level correspond to that median background level. But ultimately, that's one of the nuances. The result of that is then I stack those images after having scaled them, and this stacking process, this combination process, produces a new image. So if I want to show you what that looks like here, this is effectively the result of having done that. I can do a median, or I can do an average, basically a mean combined, if you will. And so I simply selecting the images, you can see the preview of that. So if I go back to just the first frame, you can kind of see here that might be some signal there, but then when I stack them, you kind of lose it in this stacking process here. So that was a moving signal, or it might have just been present on the first image. Now, having done that, we now want to then preview that result. So I can click on Show in Image Viewer, and this is going to show us what that looks like having subtracted this background image. So again, the principle here, the theory is that if it is a moving object, then it should imprint a signal that is greater than that of the background level. So let's go back to our coordinates there, 164.9. That's where we expect the object to be. And sure enough, it shows up a bit more clearly than it did before on the raw image. So again, if I go back to raw image, you have pretty much nothing there that you can use, but then having performed background subtraction, you start to see something of interest. Now, there's a lot of noise here. You can't just use this in and of itself. If you were to try to declare detection on every single one of these non-zero pixel values, you would be overwhelmed with false positives. So it's not yet a useful product, but it is one step further in this, what I call a pipeline of refining the raw image data. So the next step in this pipeline, what I came up with was, well, the objects that we care about appear to have a nice clustering of pixels. In other words, they're not one-off pixels, but they do have kind of a grouping of pixels together. So the next thing you can do then, and what I came up with here was you can do a convolution process. You can convolve every pixel in the image with some kind of a window of pixels. In this case, I chose a window size of 3 by 3 pixels. So the X and Y, 3 pixels in X and Y, so a total of 9 pixels in this window. And basically what that does is I'm going to compute a summation. I'm going to sum up the intensity of the pixels in that window, and then I take it one more step further and I also subtract out the peak pixel value. So this results in a new pixel value for every single pixel in the image. So let's go ahead and take a look and see what that looks like. So here you can see that's an improvement. So let's do that one more time. Here it is with the background subtraction, and here it is with the 3 by 3 convolution. So the object shows up a little bit more clearly. And what I like to do next is then show you, here it is on the next image. So the object has moved from here to here, and then the next image after that. So you can see it is moving vertically from one image to the next. Now, the object, of course, basically it had a bit more movement here on this frame because the delta time was 36 minutes, so it had more time to move from that of the previous image. But the algorithm has to be able to accommodate that. It has to be able to work with non-regular spacing from one image to the next, and indeed it does. But that's just something to keep in mind. So that's kind of what that looks like so far with this 3 by 3 convolution layer. And you can kind of get an idea now for how this process works at the detection layer. Now, the next step that I came up with was a threshold subtraction. Well, why do I need that? Well, because as I zoom out, you can see that there's still a lot of unwanted signal in the image. And so what I did was I divided up the image into groups, or into regions, if you will, different cells. In this case, I specified a cell size of 32 by 32 pixels, and so for each cell in the image, I computed an adaptive threshold. In other words, this is a way in which to suppress higher intensity regions while still being able to detect these faint objects in other regions. So here's what that looks like. If I choose the threshold subtraction, then you can get an idea for how that works. So we've suppressed a lot of the unwanted noise, but we still have our object of interest over here. So here it is, the object that we care about, and again, it still tracks pretty well from one image to the next. So that's what that looks like. The next step in the process, I thought, well, again, these objects that we want, again, they're clusters of pixels, whereas a lot of the noise is that of isolated single pixels. So I don't really care too much about those. So I wrote another function to clean up that noise and eliminate isolated single pixels. So here's what that looks like. You can see that it's removed those standalone pixels. And then finally, the next step in the detection process is to consolidate these clusters and to bring them down and reduce them into just that of a single pixel. And the way this works is I use a centroiding process. So I basically compute, it's a summation, a weighted sum, if you will, of the intensity of the pixel by that of its position, its coordinates. So you can compute basically its pixel value multiplied by its coordinates, and do this for x and y, and you wind up with a centroid for that cluster. So for example, you might have some object like this, and the centroid might not simply be the midpoint of the x and y. It might be more centroided to this region here if it has a higher intensity, for example, in the bottom right corner. But in any case, that's how that process works. So let's go ahead and take a look and see. So here's our object of interest, and now it has been reduced to that of a single pixel. Now I have retained the size of that cluster information. So if I go to frame values here, you see that we have 13 is now the new pixel value, whereas when over here it has a new pixel value of 2. Those values represent the size of the cluster that was reduced. So if I go back one step, then you'll see that we had only 2 pixels representing this cluster here, whereas here with our object of interest, it was comprised of 13 pixels. And so that extra little bit of information goes along in the computation of the quality score. So you want to wind up with as much information as you can use to compute this quality score, because the more effectively you can compute your confidence in the target, then the better you wind up with an output that has true positives at the top and false positives at the bottom of the output. So this is basically what that looks like. These are all what you could consider to be the detections in the image. So again, there's already still quite a few. Even having refined the data quite a bit, we still have hundreds or thousands of detections on every single image. But what we are able to do is at least apply a tracker, again, a tracking process to essentially eliminate all those that do not have consistent motion from one image to the next. So even though we still have lots of noise, we can still clean that up quite a bit by applying a tracking routine. So here's an example of what that looks like. If we go to track output, then I can show that here. Now I don't really need to have 10 tracks. Let's just go ahead and go back to having 2 tracks. That's the default output here. And so if I click on the first one here, the quality score was computed to be 0.341. The next one had 0.147. And these other columns, you can see its motion and its position. So here it is again, our object of interest. It was able to extract it from all of those thousands of other detections. It identified it as the most likely true detection, and indeed the most likely true track in the sequence of images. So if I want to, I can also do a max combine of the images with this track output. So here you can see, as I adjust this contrast slider again, this is that object, the motion of it. And so it was able to be tracked. You can also see that spacing, that gap, that was the 36 minutes from this image to the next image here. So you can see how that works there. The algorithm is able to, again, accommodate that non-regular interval from one image to the next. So again, a lot of this also hinges upon how effective the tracker is. So just being able to extract those detections is one thing, but being able to evaluate all of the candidate tracks that it comes up with is another aspect as well. So for that, I'll provide a little bit more detail on how that works, and then that will basically wrap up this video. One of the ways in which to illustrate how the tracking code operates is to consider a set of detections that have been extracted from a particular image. So in this case, we have image number 1, and each of the red squares corresponds to a particular detection that has been extracted from that image. Now I can go ahead and do the same on image number 2. In this case, each of the green squares corresponds to a detection on image number 2. Now, what we would like to do now is to then combine images 1 and 2, and then pose the question, what kind of candidate tracks could we establish between these two images? Now, in order to answer that question, we must first determine what is the minimum and maximum possible distance that an object that we wish to track could travel between these two images. Now, in order to know that information, we must first know what is the minimum and maximum speed of this kind of object. Now, to do that, I looked through all of the 2,000 data sets that were available in the training data, and I compiled a set of statistics, one of which was the speed of the object, and I was able to then construct a histogram, a sort of a bell curve with a cutoff points, giving the minimum and maximum speed of the comets as they travel across these images. So once you know the minimum and maximum speed of the object, then you can compute the minimum and maximum distance by dividing speed by the time elapsed from those two images. So once you know that minimum and maximum distance, then you can compute these candidate tracks. So I've given that by these yellow arrows. Each yellow arrow represents a candidate track. And so as an example here, this detection image 1 could link up with this detection image 2. However, this detection image 1 might be considered too close in proximity to this detection image 2. In other words, it does not meet the minimum distance requirement. So it would be an example of an object moving too slowly. As another example here, we have detection on image 1, but it does not link up with the detection on image 2 over here because it would exceed a maximum distance. In other words, this would be representative of an object moving too quickly. So you repeat this process for all the other detections, and then this gives you some number of candidate tracks. And then of course you do this also on image number 3. Image number 3 has its own detections, and you repeat that with linking those detections up with those on image 2. And then finally, you combine all 3 images. So here we have images 1, 2, and 3, and you start to see that there's a lot of clutter that presents itself. However, fortunately, we are able to dramatically clean this up, clean up the picture by first off eliminating single detections. So these are detections that did not link up with any other detections. So here's what that looks like. So as you see, we start to clean up the picture. The next step, we can take this a step further. We can eliminate those tracks that had only 2 detections. So here is a track. It had a detection on image 1 and image 2, but not on image 3. Same on this track. And here's a track. It had a detection on image 2 and 3, but not from 1. And same with this track. So we can eliminate these tracks here because they only had 2 detections out of 3. Now, finally, we can reduce this even more by eliminating those tracks that do not have a consistency of motion. So here's an example of a track with a nice consistent motion. It's moving pretty much in a straight line. However, here's an example of a track that has a very inconsistent motion. From image 1 to 2, but then to image 3, it almost did a 180-degree turn. And that is not typical of the kind of object that we wish to detect. So I would want to eliminate this track here, and I would also want to eliminate the track from this detection to this detection to this detection. So these 2 tracks will be eliminated, and that leaves us with only 2 tracks. So as you can see here, we went from this amount of clutter, which is quite a bit, to only 2 tracks. So tracking in general is a wonderful way in which to clean up the picture. It is able to eliminate a lot of noise, a lot of spurious detections. Now, we can also take this another step further, and basically, as I mentioned before, each track is assigned a quality score. And the way you can compute that score is by factoring in a number of features associated with each track. So I came up with a list of features for each track, one of which was, for example, the sun vector. I call it a sun vector. This is basically a number from -1 to +1. So it is a floating point value. -1 meaning it is going towards the direction of the sun, directly towards it. +1 meaning it is going away from the sun, 100% radially away from it. And 0 would mean that the track is moving tangentially to the sun. Now, track direction is a value -180 to +180 So it is simply the direction of the track in general throughout the image. Then we have track speed. We also have grid sections, so this is the location of the track in the image. Then detection cluster sizes. This is something I mentioned earlier on, where you have the size of the cluster that makes up the detection. So you might have a way to compute some value that can be incorporated into the track quality score based upon, again, the size of the clusters that make up each detection in the track. And then finally, I have detection proximity. So this is the proximity of each detection from where it was expected to be and where it was actually found to be located. So as you are tracking the object, you might anticipate that it would have a given position on a future image, and then you determine how much it deviates from that expected position. So the smaller the deviation, the higher the score, because it's meeting that expected position more closely. But as it deviates away from that expected position more and more, then we might consider that more or less a false detection. It could have been some sort of noise that happened to make it into the track. So all of these features can be used to help compute an effective track quality score. And as one example here, I mentioned track direction. So as it happens, these comets actually take on a known direction depending upon the time of year. So here it is, the month of April as one example has these two common directions, these two common direction bell curves, if you will. And then the month of October. So you can see that it has a different sort of direction. So if the track were found to have a direction outside of those statistical, these sort of histograms, then we would consider lowering the track quality as a result. So that is basically the approach that I took, all the way from detecting the object to tracking it and then computing its quality score. So thank you for watching. I hope you enjoyed this video. Again, this is now available as a module in the Tycho software. So if you wish to try it out, you are free to do so. So I will see you next time. Thank you for watching.